Let us continue. Last time, we did a very incomplete overview of inverse functions, what they are, when they exist, what they do, and we talked about how to find the derivative of an inverse function when you have a function that you're interested in and you want to find the derivative of its inverse for whatever reason. And again, wasn't a comprehensive overview. Hopefully, for those of you who have to take Calc 2, you will be reviewing that in detail. As I said, when I taught Calc 2, I spent like 4 lectures on inverse functions alone, and so we only did one. But that's because in Calc 1, we don't expect you to remember a lot, just know how to do this calculation. So ultimately, we derive the following facts. If we have a function that we know how to find its derivative, we can find the derivative of its inverse function at a specific point x if by this formula. So that was the main result. It's the big part that we care about. That's how you find the derivative of an inverse function. And of course, you might remember from pre-calculus, whenever someone gives you a function, in general you can kind of find the inverse function. Back in pre-calc, you switch x and y and solve for y. That was basically what you would do. And so you might wonder, why do we even need this formula? Why don't we just switch x and y, solve for y, and then find the derivative of that? So we're going to talk about why that might not be feasible today. But ultimately we have this formula that we can use. And we derived, using this formula, the derivative of the inverse sine function. Right? That's notation. Some people don't like the -1 notation because it also means 1 over in other contexts, but not this one. So an alternative notation for the sine inverse function is called arcsine. These mean the same thing. And to differentiate this, we found that this was 1 over the square root of 1 minus x squared. And it turns out that this guy, I don't remember if I mentioned this, but it only works in a certain range. So if your x value is between -1 and 1 and not inclusive, then that is how you would derive the arcsine, differentiate the arcsine. We also looked at the derivative of the arctangent function. So this is the inverse of the tangent function, which again, this can be stated as that. That was 1 over 1 plus x squared. And that actually worked for all real x values. So the tan inverse function is defined for all real x values, and that's how you'd actually find its derivative. That gives you the slope at any point of the arctan function. And again, every time I give you a derivative rule, there is some sort of chain rule component to it. So probably, if there is something you want to remember, is you want to remember the derivative of the sine inverse of some function u is going to be u prime divided by the radical of 1 minus u squared, as long as the output of u is between -1 and 1, not inclusive. So I probably remember that, right? The chain rule version. Similarly, the tan inverse of u, the derivative of that is going to be u prime over 1 plus u squared. So I probably remember those functions. They deal with the general case, including the basic case here, because if your u is just x, your u prime would be 1, and you recover these formulas here. So probably I would memorize those if I had to memorize only 2 of these. FYI, we're not going to do this, and neither will you be responsible, but just in case or your own edification, we can find the derivative of the other inverse trig functions. It turns out they kind of work in pairs. They're very similar. The cosine inverse, the derivative of that is actually the negative of the sine inverse function. The derivative of the sine inverse, working in the same range. And the cotangent inverse is actually the negative of the tangent inverse function. Also working in the same range. The secant inverse and the cosecant inverse, those guys are also similar. The secant taking on absolute value of x, the square root of x squared minus 1. And this guy taking on the negative of that. And these guys, they work as long as your x is not in the range minus 1, 1. So if your x is strictly larger than 1 or strictly smaller than negative 1, the derivative of these guys will be defined, and that will be the formula. Not really going to be responsible for any of these. I'd probably never ask you to do any of these, and I'm never going to ask you to do any of these. But I will ask you about the sine inverse and the tan inverse functions. Those are very common, and you realize they're also very similar to these, and these are just annoying. So in Calc 2, it's all fair game, but in Calc 1, I'd only consider you responsible for the sine inverse function. So if I want to do something in inverse trig that has a restricted domain, I'd probably give an example of the sine inverse. If I want an unrestricted domain, I'll probably give you an example of tangent inverse. And you'll see here and in Calc 2 that these kinds of expressions kind of pop up all the time. Kind of like how we were finding derivatives and the expression for e to the x popped up, right? Well, these expressions kind of pop up all the time as well. So they're very familiar, and you should be familiar with them. We derived those two formulas. We also left off with one example. We left off some examples that we didn't complete, which we will complete now. So in example 1, we were to find the derivative of the sine inverse function, and we did that. B, we were to find the derivative of this, and we did that. And C, we had another situation. So assuming we had a function that was this type, we want to find the derivative of the inverse function evaluated at the point 2. We got some more examples, but let's deal with this one first. And after this, we'll talk about that discussion as to why that formula is important. It's actually not super important in this case, but this will give you some appreciation as to why that formula is important. So let's actually do example C. So here, if our f of x is x to the fifth minus x cubed plus 2x, what would the derivative at 2 be? What would that look like? How would you compute it? What would you do? Can you tell me an expression this would be equal to? You can start there. Yeah?
Would you substitute the value of x first and then find the derivative of it after you have the value
Sure.
substituted?
What is that
So that's
look like?
2x to the fifth minus.
No. What does the general expression look like?
10x to the fourth.
No. Yes?
1 over f prime of the inverse function of x.
F inverse of what?
Of 2 in this case.
That's the first step. Your formulas are templates. Do not make a move unless there's a formula that tells you the move you can make. This is a very important concept that a lot of people just keep missing. You just start jumping in and plugging in numbers into functions. Start out by a general formula. There's a general thing that's going to get you to what you need to do. That's where you start. Start by stating the formula. The template is what tells you what to do, right? Now you go and you start to figure out what do the individual pieces in this template mean. Okay, so now in that template, I just went to the formula for the derivative of the inverse at x. Just plug in x equals 2, that's the first step, that's step 1. This is what I'm looking for. Okay, so that now gives me a goal, it gives me a bearing. I'm not going to go all over the place and do all sorts of foolishness. I know exactly what I'm trying to find here. Okay, so I realize in this formula, I need to know what f prime is. So I'll probably start by computing that. Okay, what is f prime? Yeah?
5x to the 4th minus 3x squared plus 2.
Okay, step 1. Now I know I'm going to plug something into that f prime. Specifically, I'm going to plug in the inverse at 2 at f prime. So there's something I want to plug in for x here, but I don't really know what that is yet, so now I look for that. Now, how do I find that? How do I find f inverse of 2? What does f inverse of 2 mean? Yeah?
Can't you like just switch x and y in f of x to get f prime, and then it will be x equals y to the 5th whatever, and you can plug that in place of x. I don't know. No.
Well, there's an idea to try to switch x and y and solve for y. So you have x is equal to y to the 5th minus y cubed plus 2y. How would you solve that for y? Yeah?
Maybe just plug in 2 into the inverse function.
So, first of all, this would be the pre-calc way to do it, which technically isn't wrong, but I think you can start to see the issues here. You could actually solve this one, you probably wouldn't want to, but you can kind of see where the issues are with something like this. You can see that here you would have a 5th degree polynomial in y, which we know there's no general formula that exists. That can be kind of an issue. Another thing that I could state here is if we're using this formula, we wouldn't need to do something like that, because if I was going to do this, I would have just done this from the beginning, find y and differentiate whatever that is and plug in 2. So we probably don't want to go this way, and in this case it's actually not that bad. We could actually figure this out, but I'd rather not. So that's probably not what we would do. So let's try to think of it another way. What does f inverse of 2 mean? What does that mean? Yeah?
If you plug in f of 2, then whatever that value will be, it will be the other way around.
No. Where does that 2 live? Yeah?
It's 2 equals x to the 5th minus x to x.
Right. So remember what we said about functions. Okay. So here would be a domain of our function. Here would be the codomain of our function. So we can talk about some value that f will do something, and then what we realize is that the inverse undoes that thing. Which means if you're plugging something in the inverse, it lives over here, right? The domain of the inverse function is actually the codomain of the original function, which means that 2 should be thought of as an output of this, right? Not an output of this, right? Not an input. You wouldn't plug in 2 here, right? That 2 is an output of this. So something over here is 2. And your f inverse is going to take that 2 and move it back to that original thing. So there was some x value in here that when I plugged it into f, the output was 2. I need to figure out what was that x value. In other words, if I set this equal to x, that would mean that f of x must have given me 2. That would mean that this function is going to output 2, and I need to find what x value does that. So that's what this means, right? That's what we talked about last time. Without too much help, can you tell me what x solves this? 1. So, with a little bit of trial and error, you can kind of see that 1 is going to be the answer, right? Now, when you actually solve an equation like that, I just saw it, you use the phrase by inspection. So, right, by inspection, we see that x equals 1. Now, you could technically solve this, right? You could have brought the 2 to the other side equals 0 and do a factor by grouping. Ultimately, you could get to the answer that of x equals 1. Here is why we might want to know how to do it and do this maneuver at all, right? Sometimes you get to this point and the equation that you have is super ugly. There's no nice way to solve for it. It might even be impossible to solve for it, right? And in general, you'd probably apply some method from numerical analysis or some sort of mathematical approximation machinery to figure out what x value is going to solve that or approximate the x value to some desired degree of accuracy. In Calc 1 though, you will always get a function where you can kind of see the answer. Right? You can kind of see that 1 minus 1 plus 2 should give you 2. Right? Try some nice values. X equals 0, no, too small. Maybe x equals 1, minus 1. Just try to feel around for some nice values. And ultimately you'll see here, x equals 1 seems to give you the answer. Okay. Now, getting x equals 1, we should be fine with that and moving on because we know for an inverse to exist in the first place, the function had to be 1 to 1, which means there's literally only going to be one solution that solves that equation, right? So I know once I find x equals 1, and that works, I don't need to worry about anything else, right? That's the answer. That is the answer. There's no other answer because my function had to be 1 to 1. Okay? So a situation like this is why we even need this kind of formula, because it turns out sometimes that whole maneuver of switching x and y and solving for y, or solving an equation like this, it can be literally impossible sometimes. There's no way you can actually do it. And so this formula allows us to find the derivative at the inverse at specific points, and we can do this at specific points either by noticing by inspection what would work, or by approximating this to some desired degree of accuracy. In Calc 1, you'll always be able to figure this out by inspection. Do this maneuver, get to this point, it should be somewhat obvious what x value solves for. It shouldn't take you too long to figure it out. You do it by inspection. So now that I get x equals 1, what does this mean? What does this say? Or in terms of what's relevant for us to finish this problem. Yeah.
The inverse of f of 2 is 1.
Right, so here I know that the inverse evaluated at 2 will give me 1. 1 was the guide that when I plugged it into the original function, the output was 2. Therefore, the inverse is going to take 2 and bring me back to 1. Now, f inverse of 2 is what I need to plug in here. So now that's what I'm going to do. So ultimately, this now brings us to this point. I know f inverse derivative at 2 is going to be this. I just found that this inside value is 1 from over here. And now, I need to know, this is just going to be 1 over f prime of 1, but f prime I know is this. So now I'm just going to plug 1 into that. So it's 5 minus 3, I get 2, plus 2 gives me 4, so this ultimately becomes 1 over 4. So the slope of the tangent line to the inverse function at 2 is actually a quarter. So this is a very typical problem for a quiz or a test with this topic. So you're going to be given a function, you're going to ask to find its derivative at some specific point. It starts out with this formula. What you're going to do is you're just simply going to find the pieces to plug into this formula. Find the derivative is the first step, which is just going to differentiate the original function. You need to figure out what should be plugged into that thing. So you see that f inverse of some particular number is going to give you x. You can solve for, set up this equation, and you can kind of look, well, what would I plug into this to get 2 as the answer? Or whatever value I care about here as the answer. Once you find that answer, that's your inverse output, and you come back and you plug it into that formula. And ultimately, you get the answer that way. Okay? So that's the overall strategy. Now, why this strategy would be important in the first place, why wouldn't we just, let's do like what we always did and switch x and y and solve for y? It's because there are times when that can be difficult or impossible, and so we want to do it on a point-by-point basis. So that's why we wouldn't even need this in the first place. So we kind of have this formula that can get us out of some tight situations. So it's kind of like with implicit differentiation, how sometimes you could have solved for y and just not use implicit differentiation, but sometimes you wouldn't want to, sometimes it's impossible, so you're forced into implicit differentiation. Similarly, there are some times when you want to talk about the derivative of the inverse, or you want to do calculus on the inverse function, but actually figuring out what that guy is really hard. So you get around it by applying this formula on a point-by-point basis, right? Find a point you happen to care about, and for that specific point, you can find the derivative. So we did that here, and ultimately that's how we get to the answer. So you wouldn't necessarily have to show this part right here. That's just for me reminding you what this guy means. But you kind of just go here, jump to here, and plug in. Any questions on that? And we had some other examples, a second set of examples. Example 2, where I just asked you to find a bunch of derivatives. So this was to find y prime equals dy dx. For these 4 examples, your y is the sine inverse of 1 minus x squared. Your y was 4 arc tan, your x to the 4th. Your y equals x squared plus 1, sine inverse of 4x. And you have sine inverse of x plus y. Plus y equals x squared. And I wanted to find the derivative in all these situations. Let's start with 8. How do you find y prime? Yeah.
Use the formula u prime for the derivative of arc sine of u equals u prime over factor 1 minus u squared.
Okay. And if we apply that formula, what do we get? So in other words, this guy is your u. So now what? Yeah?
It will be negative 2x over square root of 1 minus
1 minus?
1 minus x squared plus 1.
That's it. That's the answer. Just applying the formula. B. If y is equal to 4 times the arctangent of 3x to the fourth, what is y prime? Yeah?
4 times 12 x cubed over 1 plus
4 times 12x cubed over
1 plus 3 times x
to what?
whole square.
All squared. Rookie mistake here, students often will square the x and forget to square the 3. Don't fall into that mistake. So this will be 48x cubed over 1 plus 9x to the 8th. And of course, they get into that problem because, of course, they forget to use parentheses. Right? A lot of mistakes are for very silly reasons, which I tell you what these reasons are. So that's a common mistake. Forgetting to square the coefficient happens all the time. It happens because people forget to use parentheses. If you learn to use your parentheses, you'll never make that mistake. If you stop you with your parentheses, it will happen very often. Okay, let's move on. Do you need space over? That one's kind of long. Let's start over here. C. Y is equal to x squared plus 1 sine inverse of 4x. Okay, what's y prime now? Yeah,
It will be the product rule.
you need the product rule. Okay, so that's the first thing. Let's stop there. Let's pause there and really product rule. It's also very common. Every time you teach students a new idea, they forget all the old ideas. All your derivative rules, quotient rule, product rule, chain rule, everything still apply. They will always apply every single time. Once you're working with a derivative, all those rules always apply. You have one function times another function. You have a polynomial times a trig function. You need the product rule. Don't forget about the product rule and just differentiate each part and stick it together. Another common mistake. You always need to have all the rules in your mind at all times. Right? That's one of the reasons why I always quiz you about the rules. They are things you have to know. They tell you everything. Right? Really, the rules is where it's at. When it comes down to calculus and getting through a calculus class, like a Calc 1 class, if you just memorize the rules and know how to use them as templates, there's nothing else to do, really. There might come a point where you need to actually understand what you're doing. Calculus 1 isn't that place, believe it or not. If you're really smart, if you understand that thing very well that I just said, you can literally get an A+ in Calculus 1 and not understand anything. It's that powerful of a technique. The rules are everything. Never forget them. Always have them in front of your mind. They are your templates, they are your guides. They tell you exactly what you need to do. You don't even need to know why you need to do that at this point. They tell you what you need to do. Whenever you have a multiplication of functions, you apply the product rule. Doesn't matter what the situation. Doesn't matter how ugly the functions look. None of that is relevant. You have a multiplication of functions, you want to differentiate, product rule. Right? Okay. Y prime. So product rule is differentiate one, leave the other one, plus differentiate the other one, leave the first one. So what are we going to get?
F prime will be 2x times
Plus
x squared plus 1 times 4 divided by square root of 1 minus 16x.
Alright, and that's because you take the 4x all squared. And then that comes. That's right. I mean, you could probably simplify that a little bit, but I don't think it'll be worth the hassle at this point. Let's talk about the last one. How do you find y prime? Yes?
Using implicit differentiation.
Implicit differentiation. How you would know you would need to use implicit differentiation? Because your x's and y's are mixed together. You don't have like y equals some function of x. So now you know you're going to apply implicit differentiation. Applying implicit differentiation amounts to really just using the chain rule. So if you just know the chain rule version of the rules, it's not going to be any different. It's just that now this guy is your u. Okay? So we start by going through and differentiating everything. How do you differentiate this guy?
You do 1 plus y prime over square root of 1 minus x plus y squared.
First thing. Plus
Y prime
equals.
2x.
That's the first step. Now ultimately we need to solve for y prime. So now it becomes an algebra problem. So here this y prime is trapped inside of a fraction, so I just break that fraction up. And now what we're going to do is we're going to isolate the y prime. So here we have y prime times this guy. And then bring all the other guy to the other side. Now I can solve for y prime by dividing both sides by this thing. So I will get 2x minus 1 over over 1 over and that would be your answer. I can clean that up a little bit. Just to write it as a non-complex fraction. I could just, what I did was I multiplied by this guy over itself. So that's my answer. That is y prime. Okay, any questions? So in the grand scheme of things, nothing that we've been doing has changed. It's just that now we know some new functions to do it with. We now have a template for the sine inverse and the tan inverse, but nothing else changes. We're following templates just like we've always done. So that would be the derivative in this case. Now, that actually kind of finishes what we wanted to talk about there. So what we're going to talk about now is moving on to a new topic, related rates. That was the next thing in the syllabus. So that's going to be an application of derivatives that's usually applied in very a specific type of word problem. So now we're going to learn about some non-computational or not directly computational anyway applications of derivatives. It's going to apply to what we call related rates. So here's kind of the idea. Sometimes you're interested in two quantities, and you know that these quantities are related somehow, right? So, for example, oftentimes in chemistry, a volume and pressure might be related. So these are the two quantities. And you might have some relationship that connects those quantities. For example, like van der Waals equation would connect these two quantities. And so the idea is here, if you have two quantities you're interested in and you know the relationship between the quantities, sometimes you only know about the rate of change of one of them, right? So you have these two quantities and you know how fast one is changing, but you're interested in figuring out how fast the other one is changing, right? That's kind of where it's coming from. So you have a relationship between two or more quantities, right? Usually you can express this relationship in some sort of equation. And you know the rates of one of them, and you find, or a few of them, and you want to find the rates of some other one, okay? So maybe to do calculus on that specific function is going to be very difficult, but doing calculus on this one over here is easier. Or maybe it's the one that you're manipulating, right? So in the case of volume and pressure, maybe you have a way of manipulating the volume. So you can completely control how the volume is changing, but you want to see how the pressure responds, right? And you don't really know ahead of time how that's going to work, right? So that's just an example. Okay? So you have two quantities that are related via some equation. You can now actually find out how their rates of change are related, right? So related quantities will have related rates, hence the name of the topic, related rates. Right? So that's the section we're going to do now. It's called related rates. And the idea is when two quantities are related, their rates are also related. Right? And to figure out how their rates are related is not that crazy. It's just you differentiate the equation. Right? So if you can write down that relationship as an equation, just go through and differentiate that equation. Now, if you apply the chain rule, your derivatives will pop out, and now you have an equation that relates all the derivatives. Okay? So if you know a few of the derivatives, you can solve for the unknown derivatives. That's basically the idea behind related rates. Okay? So that's the overall goal here. If you quantities are related, then so are their rates. That is the prime observation here by which you can solve these. And by the way, in the case of related rates, you're always doing things in respect to time. Right, so t is going to be your independent variable. That's the guy that when you differentiate, you don't have to do anything, but everyone else, you have to actually multiply by their prime. Okay? So we've actually looked at a situation where we had pressure and volume related, and we could find the rate of change of pressure with respect to volume, the rate of change of volume with respect to pressure. But what if we wanted to find out the rate of change of pressure with respect to time, rate of change of volume with respect to time, and I only know one of those at some given moment, right? Turns out I can find the other one. Okay? So that's another thing that's important in related rates. You're always doing it with respect to time. You're finding speed in the way it's usually interpreted, right? Where time is the independent variable. Over time, how fast is this thing moving? Okay? So the idea is we can find how their rates related by differentiating with respect to time the original relationship. So that's the process of related rates in a nutshell. To apply that, you're going to have to go through a certain number of steps, which we'll talk about. So first, because there will be several kinds of applications to word problems from this point moving forward, we're not going to do everything computational. Let's just distinguish how you know you're in this situation. Okay, so on your second test and your final, there will be several problems that are word problems. How you know when you're looking at this kind of word problem. And it's two things really. A description of related quantities will be given. And some rates. Right? So I tell you, here are two things, this is their relationship, right? And then at the end of the day, they're going to say, okay, we know that this thing is changing this fast. And they're going to ask you, how fast is this thing changing? Okay? And you are asked to find one of the other rates. It's kind of a related rates problem in a nutshell. Here are some things that have this relationship. I know how fast this one is changing. Tell me how fast this other one is changing. That's a related rates. Once a problem kind of spells out that situation, it's a related rates problem. That will distinguish it from any other word problem on that test. Okay? So that's related rates. Now, once you identify something as a related rates problem, how do you go about solving a related rates problem? And that brings us to the handout that I posted on the website. I asked you guys to print out it. How many people printed it out? How many did not? Pass these around. So on the first page, I tell you, on the first page, I tell you how you would go about solving a related rates problem. Right? So in this box, you will find 6 steps that tells you how to solve it. Any related rates problem in a Calc 1 course, you can solve by going through these 6 steps. Okay? So once you identify it's a related rates problem, that these two are fulfilled, you are now going to get focused. You know that these are the 6 steps you have to kill. You are going to read the problem carefully. 1, you have to figure out it's a related rates problem. 2, you have to figure out what it's telling you, what rates are given, what quantities are given, and the relationships. 2, if possible or necessary, you are going to draw a diagram of the situation. Sometimes it's going to describe to you, you can draw a picture of the situation. And that is meant to help you with step 4 to come up with an equation. Okay? Now, it's very important that once you draw that diagram, you label it very carefully. You will label anything that is changing by a variable, label anything that is not changing by a constant. That's very important. Because ultimately you're going to take derivatives. Take a derivative of constant, you should get 0. You don't want to have a derivative floating around and you don't know what to do with it when it shouldn't even be there in the first place. You're going to write down what you know, what you want to find. Okay, so you're going to write down the rates that you already know, and you write down the rate you want to find. That sets a goal so you don't get lost in this whole mess of the problem. Then you're going to set up an equation that relates the quantities. A lot of times that diagram you set up in step 2 is going to help with this. So, you know, if the diagram happens to be, when you sketch out the situation, maybe it's a right triangle. That automatically gives you some ideas as to the equation you're going to use. Maybe it's Pythagoras' theorem, maybe it's SOHCAHTOA, sine is opposite over adjacent, right? The picture is meant to give you ideas about the equation. Once you get that equation, you differentiate it implicitly with respect to time, and then you plug in your knowns, solve for your unknowns. There will be times when you don't have enough information to do the last step, what you would do is you would go back to step 4, solve for any missing information, then come back to step 6. And all that is mentioned here. Okay, I'm just running through. Ultimately, you need to, once you get used to this, remember the things in bold, but I kind of spell out what you need to think about in the box here, so it's a little bit hefty at the moment. Another thing that you should know about is that sometimes the equation is actually just given to you in the problem itself. They just tell you, here's a relationship, here's the equation that describes it. In that event, you do not need to draw a diagram. That would be a waste of time, and usually it's not even going to be possible, right? The point of drawing the diagram is for you to help you figure out the relationship, okay? If it's given to you, you don't need to do it, okay? That being said, let's go through one of these examples. We'll go through some more tomorrow. Let's go through example 1, one of the easier examples here. I'll go through the 6-step process. You'll see how it applies here, and just realize that you're pretty much going to do the same thing all the time with any related rates problem. Okay? So the word problems, again, they're like templates. Step 1, step 2, step 3. You go through all these processes. Pretty much always do them in the same order. And again, sometimes you can skip step 2 if step 4 is given. So let's look at example 1. First step, read. A lot of people miss a lot of important information because they don't read properly. 2. Okay. So, first step, read. Okay, a right circular cylinder undergoes expansion. Okay, its radius is increasing at a rate of 1 meter per second. Its height is increasing at a rate of 2 meters per second. At what rate is the volume changing when the radius is 1 and the height is 3? Okay, so here they described some related quantities, the radius and the height of a cylinder. Right? They told us how these things are, how fast they're moving, and it asked us how fast something else is moving. You see? So they tell us the radius is moving this fast, the height is moving this fast, how fast is the volume moving? Okay. So you can do a diagram. Now the diagram is really just meant to conjure up some old equations that you would have learned in high school geometry. So perhaps you saw a diagram of a right cylinder. You realize that the radius is here. I would label that R because it's changing. Height would be here. I would label that H because it is changing. And that's going to be my diagram. 3. You're going to write down what you currently know and what you want to find. Right? You need to answer this question. What we know so far is how fast the radius is changing and how fast the height is changing with respect to time. Radius is increasing by 1. Increasing means the derivative is positive. The height is increasing by 2. Increasing means the derivative is positive. If they told me decreasing, I would actually put a negative quantities here. What do we want to find? Well, I want to know what is dV dt, how fast is the volume changing when R equals 1 and the height equals 3. So once you get that, you can now forget about the problem. Now you're focusing on these. Okay, so 4, you are going to come up with the equation that relates these quantities. Does anyone know how V relates to R and H from a picture like this? Yeah.
V equals pi r squared h.
Pi r squared h. Okay. This is what you call, once it's a right circular prism, the volume of a prism is the area of the base times the height. That's always what it's going to be. So the area of the base is pi r squared times the height is h. That's your relationship. Okay. So 5. Now you're going to differentiate with respect to time. What's the derivative of v with respect to time?
dV.
That's your dV dt. Okay, differentiate this with respect to time. Yeah,
So you do the product rule, and
you would need the product rule, still a thing. R is a function of time, so is your h. I have two functions multiplying. Product rule applies. Okay, so, all right, let's differentiate the r part. What do we get?
2r drt.
Right. So we get 2 pi r dr dt. Leave the h alone. Plus
Pi r squared dh dt.
pi r squared dh dt. Now, this is the guy I want to find, dv dt. And hopefully by the time you get to this point, that's the guy I want to find. Hopefully by the time you get to this point, that brings you to step 6. You can solve for what you want. Now, hopefully, by the time you get to this point, as I was saying, you actually know all the pieces to plug in. In this case, we actually do. However, if there was any point where we didn't know something, I would simply go back to this equation and solve for something. Right? The problem would give me enough information to do that. But at this point, now I'm just going to plug in 2 pi times r. R is 1 times dr dt, which is also 1, times h, which is 3, plus pi times r squared, r is 1, times dh dt, which is 2. So ultimately here, I get 6 pi plus 2 pi, which is 8 pi. This is meters cubed per second. I usually won't care about the actual. It's not a physics class. I don't care about the units, but the quantity is going to be important. The quantity and the sign of the quantity is what I care about, and that's it. We'll do a few more. You'll realize we can go through these 6 steps all the time for all of these problems, and we'll pick up with that